Chapter 6, structural. Okay, in chapter 4 to chapter 5, we talk about rigid body, we talk about moment, but most of them we're talking about single member or dual member. However, that's not going to be the case we encounter in most of the mechanical engineering problem or civil engineering problem. In most of cases, we're going to have multiple components or members joined to the same structure. So, for instance, when you drive I-79 from Pittsburgh, I think it's going to be somewhat curved to Cleveland or area. So you are going to encounter a few rivers, and you're going to see the bridges on the highway. They're going to look like this. Like that, right? You see this a lot, right? I think there are 3 or 4 along the highway. So when you see those kind of things, do you think you can analyze those kind of things yourself? It's actually pretty straightforward if you know the techniques. Those members in the structure has their own meaning, because some of them are just used for redundancy because of safety consideration, and some of them are actually have the consideration of supporting forces. That is something we're going to talk about in this chapter, and this kind of structure we call it truss. Okay, so we're going to talk about how we analyze those things and how we use the method we learned in previous 2 chapters to analyze everything we have here. Okay, and in this kind of structure, we need to know 2 things. One is external forces. One is internal. Okay. Depending on what we're talking about, the forces needs to be identified differently. For instance, most likely, if it's a bridge, it's going to be something like this, because the ground surface might be moving a little bit, so we don't want to fix the end over here because it might destroy the whole structure. So normally we will fix on one end and have those kind of normal contact at each end. So when we try to analyze something like this, we treat the whole system as a whole. So in that case, what do we have? We don't need to worry about the structure, the internal structure at all. We only need to worry about the joints over here. So based on what we learned in chapter 5, this is a bearing joint. So we're going to have 2 forces over here. Let's name this one A, B, C, D, and E. So if you don't consider all the bar in between, this is just a big block. So when it's a big block, this is bearing over here. We're going to have A, Y, and AX. How many forces we have at B? 1, 2, or 3? 1. This is a normal contact. So what kind of forces we have here? Horizontal or vertical? Vertical, right? So we have y over here. How about c? Vertical, right? And same for d. And e. So before we start to analyze what kind of forces we have in the system, you always need to use a technique you learned in chapter 4 and chapter 5 to figure out what are those forces is going to look like. And those forces are external forces because those forces are provided by the supporting surface. So which means when you are doing, before you start to do the internal forces, analyze whether the whole thing is going to crush this part, or this part. You always need to know what are the external forces it's going to apply to my system. Does that make sense to everybody? Okay, so but most likely you're going to find some of the forces is going to be very straightforward to find out, which is, in this case, what you can see is equals to 0. This still fulfill the regular method or concept. We have fx equals to 0, fy equals to 0. So in this case, which force equals to 0 automatically? Ax, right? Because there is only one force over here. And you're going to find I have 1, 2, 3, 4, and 5 forces over here. Does this going to work? Obviously not, right? So you might need to take few moment center. For instance, over here, then take this one. Of course, we know ay plus by plus dy plus dy plus ey equals to what? 0. And you also know this is not going to be rotated. So if you put your moment center over here, those two forces with a specific combination is going to equals to 0. So you might use this one or another one again. So you have 3 equations, then you use this one again, then you have 4 equations. Then in that case, you might be able to solve all the unknowns over here. Then after we figure out all the external forces to the system, then we start to talk about what kind of method we're going to apply to this kind of truss structure, so that we can identify what are the forces applied to individual components. Okay. If you download the notes from website, you're going to find there is something called statistical determinacy on one of the pages, but this thing is not discussed in the textbook you have. This is a very handy method to determine whether your system is going to be stable or is actually very shaky. So for instance, you have 3 numbers. This is number. Members. This is number. Joints. This is number. Reaction. Components. Okay, so I'm going to explain to you what this is going to look like. So if it's two-dimensional problem, R equals to 3 always. Okay, because you have, well, this is by definition. So just keep in mind R equals to 3 for two-dimensional problem. Now, we have 3 cases. We can only have 3 cases. One is if they are equal. If this number is smaller than this one, or this number is more greater than this one, we can only have those 3 types. So what does that mean? M means the number of members. In this case, how many members we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's straightforward. You just count the number of members. You get the how many joints we have here? 1, 2, 3, 4, 5, 6. Okay, so everybody understand how I get those numbers? So if they are equal,
How do you get the numbers?
the what?
The numbers.
The members 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you just count it. There is no hidden technique here. Just count the members, and you also just count the joints. Here, 1, 2, 3, 4, 5, 6. That's it. So if this one, if they are equal, it means that this is internally stable without redundancy. It means that if you have a structure like this and you have external pulling forces on top of this thing, you're not going to change its shape or its structure. It means that it's stable. Okay? If this number 2j smaller than n plus r, it means that it's stable, which means you're safe. But you do have redundancy. Which means you are wasting your material. But you can argue that this is for safety. Okay? But if your 2j is greater than n plus r, it means that it's internally unstable. I'm going to show you different cases. How many members we have here? The circle over here means the joints. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 members, which means my M equals to 10. My joints is 1, 2, 3, 4, 5, 6. J equals to 6. So based on the configuration over here, M plus R equals to what? 13. And 2J is what? 12. So it means that one of the bar can actually be removed. Or even you remove this bar or this bar, they can be saved. Does that make sense? If I have something like this, how many members I have? 1, 2, 3, 4, 5, 6, 7, 8. No. J still equals to 6. So m plus r equals to 11, 2j equals to what? 12. So this is internally unstable. So if you put forces not necessary to be at those two locations, but other locations, it is likely this one is going to be collapsed. Okay. Let me do more examples over here. Well, this method is kind of handy, but it cannot guarantee it always do its job. Reason is, well, you can have over complex structure over here, but over here you just leave one bar. So it has some kind of a defect, meaning that if you put something like this, if you remove this bar, but put another bar over here, mathematical wise it's fulfilled, but practical wise, it is very likely you're going to break the whole thing. So I guess that's a reason this textbook doesn't want to use this method, but this is some kind of, if you think some people really spend his time designing his structure and you just want to evaluate whether it's going to be stable or unstable, this is going to be a quick method to evaluate that. But as I said, if you have some place which is over complex, but there are some place which is overly simplified, then this method cannot do its job. But anyway. How about this one? How many members we have here? 1, 2, 3, 4, 5. 5 members. So how many joints I have here? 4. So this one n equals to 5, j equals to 4. Is this internally stable or internally unstable? Stable. So without redundancy or with redundancy? Without. Okay. How about this one? How many members we have here? Okay, how many joints we have here? 5. So is that internally stable or unstable? M plus R plus 3 equals to 8. 2 multiplied by j equals to 10. So is that internally stable or unstable? Stable. Unstable. So if you push over here, it might push to the other side. If you press from the top, it might go inside. So this is internally unstable. How about this? 1 m equals to 1, 1, 2, 3, 4, 5, 6, 7, 8. My joint equals to 1, 2, 3, 4, 5. How about this? 8 plus 3 equals to 11. J plus j multiplied by 2 is 10. So is this stable? Okay, this is stable. So does this with redundancy or without redundancy? With redundancy, which means you can tell your boss you are considered safety, or your boss can actually scold you. You're wasting your material. So either way, depending on who you're talking with, it can determine what kind of word you're going to use. Okay. Okay, yeah, we're going to talk about method of joints. So now we know how the external forces is going to affect my structure, but how do I determine the forces going to apply to individual components internally? We have two methods. One is method of joints. when I have a structure like this, the first thing you need to do is you have P, apply a B. So the first thing you need to do is do what? Treat everything as a whole system and figure out how much force you need to provide at point A and point C. Those are analysis for external forces. Okay, you wouldn't be able to tell how much force has been applied along AB, BC, and AC. So when you finish this analysis, keep in mind this is the most important thing you need to do in the first step. If you don't know how much force has been applied at individual joints, you wouldn't be able to analyze the rest of the problem. Okay, so after you're doing that, you're going to decouple everything into 3 members. Now, when you have bar AB, how many points I'm going to apply force on this specific member? 1, 2, 3, or more. How many points I actually apply force to this thing? 2, both ends, right? So based on chapter 5, what is this? 2 force member. When it's 2 force member, what do we know? The force must be what? Same direction, but no. Same magnitude, but opposite directions along the orientation of the bar. We just talked about that in the beginning of the class. Do you guys still remember that? So, with that said, I can say, okay, I might have some force over here, I have force over here. Let's say this one, do I have FAB? Over here. And over here, I have the same thing, but this time I name this one FBC. FBC. Over here, I have FAC. FAC. Okay? But when you apply to this joint over here, which means it's over here, if you cut this, what happened? Are they, when you cut, when you separate those two things apart, are they going to move suddenly, or are they going to rotate suddenly? No, it won't move, it won't rotate. It will remain everything like this, just like the stable, which means over here, the total force applied to this point equals to what? 0. The moment equals to 0. So with that said, that's also something we call Newton's third law. You have force FAB to this one, you have FBC to this one. They're going to be opposite direction, but the same magnitude. The force applied to the member. And over here, of course, we have P, the external force applied to this thing. Does that make sense to everybody? Okay, so we're going to do the same thing for joint C and joint A. So for joint A, I have FAB towards to this direction. For sure, I need to have another force forward towards to this direction. And I have FAC to this direction. I must have FAC to this direction. Same here and here. Okay? Those 2 points, those 2 joints over here, they have their own external force. You need to draw them as well. Those forces need to be solved in the very beginning when you start to draw the free body diagram. Okay? If you do this, you're going to find AC actually equals to 0. So just remove this thing. So what's that step? You start to analyze the force, the combination of forces at this point, and this point, which means you're going to solve for 3 equation of equivalent for point A, point B, and point C. Okay, so for point A, I would say join A. What do I have? It's going to be FAC. Based on your configuration over here, it's positive direction. And let's say this is theta A. I must have minus FAB cosine theta A equals to what? Is this joint moving or rotating at all? No, so what is this going to equal to? This one equals to 0 as well. So most likely, I'm not going to give you over complex problem when you are doing the homework or doing the exam. Not homework. Not in the exam. So most likely you're going to have two unknowns in the equations, but you should be able to find out the numbers using two equations. Okay. Same for joint B and joint C. We don't need to consider moment equations because all the forces are applied to the same point, which yield the moment arm equals to 0 for all of them. So for individual joints, the only thing you need to worry are two equations, fx and fy, and both of them needs to be equals to 0. Does that make sense to everybody? Okay, so calculation-wise, it should not be that complex because you only have two equations, and chances that you're going to have at most 3 unknowns involved in this kind of equation. But keep in mind, you will need to treat the system as a whole when you approach this kind of problem and find out all the external forces before you break that into individual members. Okay, that's the most important thing for this kind of problem. And once that's done, you just do that for two equations. It should be okay. Okay. Okay, let's take a break. 5-minute break. Be extended. So, or under compression or under tension. So over here, if you find out both FAB and this FAB is positive, which means the direction is correct. Your assumption of direction is correct, right? So when the assumption of the direction is correct, of course you're going to see this one is actually to this direction, but based on Newton's third law, this actually go into this direction. So when you have this kind of configuration, is this bar under compression or under tension? It's going to be like this. You have a bar, you do something like this. So this is going to be under compression. And over here, if FAC, you do the assumption is correct, means that FAC doesn't have a negative sign in front of it. Both force of FAC is going to extend this thing, so this bar is under tension. So in this kind of problem, I'm not only asking you whether how much the force has been applied internally, I'm also asking you whether it's under compression or under tension. You need to answer questions like this. Okay, we're going to work on one of the examples and explain to you guys. But before we move on, the procedure is step 1. Of course, you need to identify what are given and what you need to find. Right? Step 2, treat the whole system as a whole. Draw rewrite diagram. Step 3. What do we have? The same. Step 4. So pretty much, the first four steps are something you deal with. The procedures you deal with the problems in the previous chapters. You need to do everything. Then you move on to the next step of identifying the forces internally. So you need to draw free-body diagram for joint and members. All of them. Step 5, step 6. In this case, what do you have? You only have two equations, as I said. We only deal with the force at the joints. That is something we call method of joints. Okay, you don't need to worry about the force in over here, because we assume the force for applied to this specific member, they are the same magnitude but opposite directions. So in this case, the force is always 0, and then you're talking about the same force. So we don't do the equation of equilibrium for the member. We deal that at the joints. Okay. Okay, so you need to solve the forces of individual members, and those three steps may be required to repeat themselves a lot of times, depending on how many joints you have. But normally, if you say you have 3 joints, you only need to solve for 2 joints, because the third joints, you don't need to worry about it. You always use the last joint to verify whether your answer is correct or not, because at that moment, most of the numbers have been derived. The last joint is only used to identify whether your answer is correct or not. Okay. Once this is done, then the last step, normally you would need to determine the compression tension status of all members. If you need to take mechanics of materials, you might need to answer what kind of material is strong enough to support the structure like this, because you do know how much force has been found internally. So you need to determine which kind of material you should apply to this kind of structure, so the system is not going to be destroyed when you have a load specified in the problem statement. Okay, so it's not, compared to the first part, I wouldn't say the difficulty is going to increase, but it is going to be much more tedious. In particular, if you have more than 3 joints, then you might make mistake while you're doing something over here. But keep in mind, work that into individual points, and don't think this is really complex. Just repeat those kind of things individually. If it's in the exam, you do have some concern of calculation error, don't worry about that too much, because as long as you show me it's correct procedures, you're going to be fine. Okay. Normally, I'm gentle to the calculation errors, As long as you are not copied from other people's value, you should be fine. Okay. Okay, so I have a structure, I have truss like this, and I would need to determine the force in each member of the loading like this. So I'm going to basically follow the procedures over here and get all the information from this structure. Okay, so I'm given a truss. And I need to find forces each member. Okay. So what is the first thing I need to do? Do I break that into individual joints at this moment? What do I do? Free-body diagram of what?
Everything.
The whole thing. Okay. So I'm going to do step 2 to step 4 and identify how many external forces I'm looking for over here. 1, 2, or 3, or 4. 2, right? Force at A and at C. That's the only thing I need to do. So over here, I have just treat the whole thing as a triangle. And there are 2 forces given at point D and point B. They are 300 pounds over here and 1,000 pounds over here. What kind of forces I need to draw my free body diagram at point A? 2 forces with 1 moment, or 2 forces, or single force. Which directions? Of course, it's going to be X and Y, right? So I would use the regular coordinate to do everything. How about point C? Am I going to use 1 force, 2 force, or 2 forces with 1 moment at C? Is the force horizontal or vertical? Okay, it's vertical. So that completes my free body diagram. So when I do my free body diagram, I have 2 equations: fx equals to 0, fy equals to 0, fz moment equals to 0. So at this point, fx equals to what? Ax plus 300 pound equals to 0, which means Ax equals to negative 300 pounds. Nothing fancy, just very typical procedure. Fy, I have an external force 1,000 pounds downward. I have 2 forces, Ay and Cy. This equals to 0. But I have 1 equation, 2 unknowns, which means it's very unlikely I will be able to know Ay and Cy based on this equation. So I would like to use the moment at A. So this 1 mass equals to 0 as well. But most of the guys are going to make a mistake over here, because you know it's going to be 1,000 pounds multiplied by 4 feet. Is that positive or negative? Negative, because it's clockwise. You're going to have Cy multiplied by 7 feet, positive or negative? Positive, because it's counterclockwise. Anything else?
300?
Yes, that's the most mistake you guys are going to make here. 300 also need to be considered over here. So you have 300, very good. Multiplied by, what is the moment arm? 3, good. Don't say it's going to be 5, because it's perpendicular to the force, so it's only 3 in this case. Okay, is this positive or negative? Negative. Equals to 0. So in this case, can you find out CY? It's going to be 4,000 plus 900, so 45 or 4,900 foot-pounds, and this is 7 feet, which yields if you know AY equals to 700 pounds, AY mass equals to 300 pounds. So far, any question? So this complete the first 4 steps of solving this kind of problem. Any question? Is that clear? Everybody understand what I'm talking about? If I give you something like this in the quiz today, you'll be able to solve that? No? If you say no, then you're in trouble.
For the 300-pound force, why is it times 3? What, down when you're finding the moment?
This one?
Yeah, why is it times
Because the moment I'm over, because I forgot to write it. It's 3. It's in the problem. It's in the notes, but I forgot to put it over here. It's 3 feet. That's my bad. Okay. Yeah, I'm going to do how many joints I have here. 1, 2, 3, 4. So I can tell you I need to solve for 3 joints and use another one to verify whether my answer is correct or not. So I'm going to do 4 times, but you actually just need to do 3 times. You should be able to find out all the numbers. Okay? I'll show you why is that. Let's do joint A. So for joint A, I know my vertical force is going to be what? 300 pounds. I know my horizontal force is negative 300 pounds, which means it's going to be something like this, right? Now, how many members I have connected to joint A here? 2, right? So we need to have 2 forces from member AD and member AB. Okay? But with that said, do we know the direction of member AD and member AB? We do, right? Because AB is horizontal, which means, and this is 2 force member, which means the force must be this direction or this direction. AD must be this direction or that direction. So we just need to do our assumption over here. So over here, I would assume this is my FAB. And since I have a force, over here like this, and the orientation of AD is 3, is 4, this must be what? 5. Okay, so we should be able to figure out the direction of FAD from here. So, as I said, we just need to have 2 equations, Fx and Fy. In this case, it's going to be negative 300 pounds plus FAB minus FAD multiplied by 4 over 5 equals to 0. Fy equals to 300 pounds minus FAD. Any question for this equation? For those two equations, how I get these two equations? Okay, so based on this thing, can we figure out how much force we actually have for FAD? Mass equals to 500 pounds. Do I have any sign I need to correct in front of it, FAD? Yeah, which means my assumption over here for FAD is a correct one. Okay, so since we know FAD equals to 500 pounds, put it back to here, we're going to get FAB equals to 700 pounds. Yeah. 700 pounds. And those two are the answer for my internal forces for this member and this member. Is that clear? Everybody understand what I'm doing? Any question? Seriously, because this is going to be in the exam next week. If you don't know what I'm doing, you're in big trouble. This is going to be the major thing in the exam. And at least one of the problems is going to be something like this. Then I'm going to move to joint B. For joint B over here, how many forces I'm expecting? Here, 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 and 1,000 pounds, right? And we do know this is given. We have three other forces. They are force BD, force BC, and force AB. Do I know the direction of FAB at this moment? We do. We also know its magnitude, right? But what is the direction? Now, at this moment, I need to ask you, is if member AB moving or rotating? No. So, when you apply the force to this bar, they must be the same magnitude, but opposite direction. Everybody agree with me? So, since I know it must be the same magnitude, opposite direction, can you determine the direction of FAB when you draw the free body diagram over here? It must be something like this. Make sense? So now, what is the force FBD? Can you assume its direction? Are you going to assume it's downward? Or it should be upward. It should be upward, right? Because we try to make this point or this joint not moving, not rotating, which means the force must be compensate for each other. So over here we have FBD, and over here I have FBC. Something like that. Any question? Is that straightforward? Everybody understand what I'm talking about? So the next thing we are going to do is doing right. Is that clear? Everybody understand what I'm doing over here? I'm not doing anything specific. I'm just draw the free body diagram first, and I draw the known forces from the problem statement, and another force I derived from the previous joint. So putting them together, I also found two other forces are both in horizontal direction and vertical direction. So in that case, we should be able to identify the forces from the configuration over here. Okay. Yeah. What else? Joint C. Okay, so for joint C, we have one force that we derived from the very beginning. Over here, that is my CY. That is going to be upward, 700 pounds. Right? What else? Over here, FBC is something we can get from the configuration, but opposite direction, which means I have my FBC equals to 700 pounds over here. What else? A force from member DC. I'm going to assume it's going to downward like this because if you break this into horizontal axis and y axis, it's going to compensate for this one and this one, both of them. So, can you determine the angle of this thing as well? It's going to be what? This is with 3B, this is 3B, so angle over here must be what? 45 degrees. So we're going to do the same thing over here. Fx equals to FDC cosine 45 degree minus 700 equals to 0. Fy equals to FDC negative sine 45 degree plus 700 equals to 0. Of course, they must agree. If they are not agree with each other, you're doing something wrong. So FDC is going to be 700 over cosine 45 degree or sine 45 degree. It's up to you. And get this one equals to 990 pounds. So at this moment, we know the force over here, we know the force over here, we know the force of this part, the force of this part, and the force of this part. We pretty much know everything. But what's the next? I'm going to erase this part. So the next thing, if you are doing this at home, I would suggest you do verify your answers. So what you're going to do is to use joint B used to verify your answer. So over here, what do I have? I have 300 pounds from the problem statement. And I have FEC to this direction, which means I should have a corresponding 990 pounds in this direction. And FBD at joint B is point upward, so in this case it must point downward. FBD, that is going to be 1,000 pounds. What else? I should have FAD over here from joint A. FAD equals to 500 pounds. So the next thing you're going to do is put everything together and ensure everything equals to 0. If they're not 0, you're making some calculation wrong. So over here you're going to have So it should be 700, which is equals to this number. That is U. Fy equals to 990 sine 45 degree. This will give you about 700, and plus 500 multiplied by 3 over 5. This is 300. So 300 minus plus 700 equals to 1,000. You do have another negative 1,000 over here, which verify all my answers are correct. Does that make sense to everybody? Now, the very last thing is to determine whether I have compression or tension for individual components. Okay, so at joint 8, I have 300. So it's kind of draw all the configuration into